Hey, welcome to the tutorial of HVAKR's new and improved System Configurator. Really powerful, fully modular and modal, very custom. And here I'm going to go over all the ins and outs of how this works. We'll talk about how to set up these diagrams, how to select basic systems. I'm going to get into each component, how it works, what the inputs are. We'll get into some advanced system setup, presets, what those do, different modes, how to work those, the reports, of course, how to see your results and manipulate them, and then also how all of this ties into air balancing. So without further ado, let's get into it. First things first, before you get to configuration where you see this line diagram, where does all this come from? It comes from your zoning. So after you've created your spaces, modeled your building, you're going to do your zones. You're going to group those spaces onto zones. Then you're going to group those zones into systems like this. We'll call this system A, and I'll assign 1, 2, 3 zones here. And now when I go to configuration, there's system A with the zones that it serves. I can even expand these zones to see the spaces that they serve as well. Okay, now we have this structure, and configuration is all about, quote, selecting your HVAC system. Except in HVACR, we do it differently. We don't care what you call this. There's not going to be a big drop down. Yes, we have presets now, but really we encourage engineers to model their systems by going through the airstream and setting up the processes themselves. It's a first principles approach. We don't care what you call this as long as you have modeled what is happening to the air as it goes from this central equipment to the terminal units, zone level equipment, then finally to the spaces. So as long as you set this up per your design, you're going to get solid results because it's all about those processes and the pure psychrometrics. Huge concept. If you understand that and you can put yourself in the place of the airstream, you can set up any system that you want. This is huge because it makes the coil calculations transparent. This step is no longer a black box. You can see exactly what's going on based on exactly what you set up. All the data is here. You can see how much airflow is coming into each component, going through, and then we've even paired it with the psych chart so you can see exactly what you've set up. Outside air, mixing what that state is, this process, that process. It's all plotted here, so you make sure, yes, these numbers look good. This is exactly what I'm designing for. So how does this work? You basically have two tiers. The central or system level tier, this is a box, and you can add components to this level. It's going to be serving the second tier, which is your zone level equipment or your terminal units. In HVACR, we call this a central unit. We call these terminal because they are kind of the last or the terminus before the air ultimately goes to the spaces. Now, at each level, you have the opportunity to configure processes. I'm going to start from a blank slate here and walk through the components that you can configure. Later, I'll show you the presets and what those are made for. But if you understand these fundamentals, you can build whatever you want. So when you select your box here, this is the central unit, you can add components. When you go to add components, you have these options: outside air intake, an energy recovery ventilator, basically an energy recovery process, return air intake, a cooling coil, a heating coil, and then also a fan. So you can add fan heat somewhere in the middle of this process or at the end, wherever you want. Let's go ahead and just add each of these components so that I can walk through what they do. Okay, there we go. You have the same options when you go to the terminal unit. So you can have processes happening here, and then at the terminal level, before it is supplied to the zone and the spaces within that zone, you can also add the same number of components. But we'll demonstrate at the central level what each of these does. I'll also note you do not have to place the components in this order. This is fully modular. If I wanted, I could bring outside air intake over here after the return air. I can take this and I can disable that component in cooling mode, such that in heating mode, I might want it enabled. That's the kind of flexibility we have. I can outright delete it from the process. Later, I can always add it back and put it in the place that I want it to. So we're no longer bound by a specific order of things, although most systems do follow a kind of logical order. So let's take this back to kind of a standard positioning. First, the outside air intake. Now, each of these components, the inputs are with the component. So in order to adjust the inputs for these, you would click on the component, and you'll see some options. So outside air intake is just that. It's the amount of outside air that's coming in to this component. At the central unit, this is going to be common for like multi-zone systems or DOAS. Most of the time, the outside air comes in at a central level before it gets distributed. And then here are really our only input is what is the outside air method. So with this, I have some options. Sum of spaces will give me just the sum of the required ventilation for all the spaces within this system. Percent, I can specify this as a percent of the primary air supplied to the spaces. So basically it's like the design supply air, usually load driven supply required. It's going to be a percent of that. It's not a percent of the air going into or out of this box. It's a percent of your primary supply. Then custom is just, hey, put in whatever CFM you want. And then multi-zone is great for VAV systems. This uses the ASHRAE 2025 62.1 multi-zone methodology with diversity applied and all that, zone ventilation efficiency to basically adjust your outside air intake for a multi-zone system. So those are the options. Next, the ERV component. The input here is effectiveness. So you put in your ERV effectiveness, and that is used to determine how efficient this ERV is, and it will temper the air coming in. The exhaust air present in the system is what drives basically the exhaust air going through one side of the ERV, and then your outside air is going through other side. Following that, we've got return air. So this is our return air component. You can turn relief on or off. When you apply return air to a central unit, the default is that relief is on. And in that case, it is going to basically determine if there is a differential between your outside air, your return air. It's going to relieve air to make way for your outside air. Now, in some systems, you already have exhaust present and you have less return air than supply going out. And relief may very well be 0, but basically this is going to relieve the return air to make way for your outside air unless you were to turn relief off. Additional, this is miscellaneous really, is you can apply return duct leakage and return duct heat gain or loss to adjust the state of your return air before it gets back to the unit. Next, we've got a basic cooling component. So the key input here is your off coil temperature. What is the cooling supply air temperature that you want this component, this coil, to achieve? Let's say it's 55. Awesome. So after everything happens here, this coil is going to bring whatever state air enters it to 55 degrees. You'll be able to see the load associated with that. You'll see all the psychrometrics associated with that. You can also apply a coil type, just 2 basic ones. DX basically just documents this is a DX coil, right? If you have chilled water, then an additional input will become available. You can choose your chilled water delta T, and then we'll also calculate the GPM for your water based on the load on the coil and then what that delta T is. So it gives you a little more information. This is not required, but this is going to be fundamental to understanding, okay, what supply air are you providing to the spaces, and therefore what's the CFM we need to supply. Heating is very similar. This heating coil, you want to provide your off coil temp for this heating coil. We have a couple options for heating as well. Really, DX, gas-fired and electric, it's just to document kind of what the design intent is. But then with heating hot water, same deal. You can apply a water delta T, and it will return a GPM in your reports. I'm going to stick with, let's just say gas-fired for this case. And again, you would apply your heating supply temp. Finally, we have fan heat, and we can just set BTUs that you want to add to the airstream. Another option is temperature rise. You can set how many degrees this is going to increase the temp of the airstream. And again, you can place this before the coils, after the coils, wherever you want this state change. It's important at this point to note that this configuration is now modal. We have a cooling mode here and a heating mode here. So all of this setup I just did, I did in cooling mode. If I want something similar, if I want to share components in heating mode, I would have to go to heating mode and I would enable those components in heating mode. So cooling, I might have something like this. Let's pretend I'm designing just a package rooftop unit, single zone. I'm not going to have any processes happening downstream of this central rooftop unit. In cooling mode, I may have outside air intake. Let's go ahead and get rid of the ERV. I'm going to have return air coming back. I'm going to have this 55 degree cooling coil. Here, I'm going to disable the heating in cooling mode. We won't have a heating process in cooling. And sure, let's keep the fan heat gain. Now, in heating mode, I want to make sure I still have that outside air intake. I have the return air, and instead of the cooling coil, this time I'm going to enable the heating coil there, and I'll just go ahead and leave the fan heat disabled so that I don't apply a credit to my system. I'll be a little conservative here. So now if I toggle between cooling, we'll see, all right, I've got cooling coil with fan heat being applied. In heating mode for this system, same mixing. This time my outside air is winter condition, but I have the heating coil at 90 that's going into effect. So you do have to pay attention to what mode you are designing for, and you have to make sure it's configured for both. Now, let's talk about the psychrometrics and the airflows. Where do those come from? So psych chart first. If you hit this expand button, you'll be able to see your configuration next to the psych chart. So here's that outside air state, again, cooling mode, which means summer conditions. Here's the return air state, which is basically my space set point. And based on the outside air ratio, the airflows, this is the mixing state. This is going to get conditioned down to, I said 55. In this case, I'm not quite hitting the dew point. And then a little bit of fan heat gain brings it back up to this 56. This is the air that is entering my spaces. So if I hover over supply air, I'll see that there's 1,960 CFM of supply. Where is that coming from? Well, let's go ahead and click on one of these spaces that is served by this system. This particular space, 390 CFM of supply, and if I look at the airflow data here, I see 390 is my design. If you scroll further down, you'll see total space sensible and your load determined supply. So this is just showing you what your total space sensible load is, and then this is the load determined supply. This is based on the state of air entering this space, which, because I don't have anything configured for the terminal units yet, it comes straight from this. Dry bulb 56, wet bulb 53. This is downstream of this fan heat, but then also this cooling coil. So this is what drives the temperature of the air entering this space, and that's used in the calculation with your total space sensible to determine what the CFM required by the space is. So you take that for the spaces served by this system, and you actually take the peak of the system to determine, okay, this is the primary supply air coming off this unit. And just to demonstrate, let's look again. 390 is the design driven by 388, which is load determined. If I were to take this cooling coil and drop this to 50, now we go from 50, we raise it a degree with the fan. We are now leaving the unit at 51 degrees, and you'll see already my primary supply has reduced because I'm supplying colder air. Going back to this one space, it went from 390 to 300 because there's colder air entering the space. Load determined does not always drive your primary supply. If the required outside air is greater than your load determined supply, that may drive your design CFM. Or if you have alternate requirements, like just a minimum requirement, that may also drive it. So when it comes to airflows, when we're looking at this and looking at the psychrometrics, this primary supply airflow, ultimately, if you follow all the way down, comes from load determined supply, which is based on the total space sensible, unless your ventilation requirements exceed that. Now, let's look at how air travels from the central level to the terminal level. Right now, I have kind of a basic RTU configuration, and in cooling mode, it is doing all of the cooling. Let's bring this back to 55, and in heating mode, I'm going to go ahead and let's just delete this heating coil. So right now, this central unit, I just have outside air mixing with my return, and that is going to be supplied to these terminal units. At this point, it's worth showing you this trick. You can configure all units together if you select them like so. So I could even do this with all my central units. I could configure them all the same way. One time, I don't have to do this individually for each box. So these terminal units, I'm going to select them all, and then I'm going to configure them together. In this case, let's say I just have a VAV with reheat. I'm in heating mode. So cooling mode, it's not going to be doing anything. It's going to take the cold air straight from the central unit at 55. Heating mode, I'm now looking at these terminal units. We're going to add that heating component. And in heating mode, I want to make sure whatever comes from the central unit, my final heating temp gets up to 90 degrees in this case. So now these are all configured that way. Fantastic. Let's look at this one here. State 1, if I look at this, it's 100% of supply. And if I look at the psych chart for this, there's my state 1. It's 43.8 dry bulb, 39.8 wet bulb. Where does that come from? All right, let's back up. Central unit, that's upstream of that. Let's look at the psych chart there. All right, this is where it's coming from. Outside air in the winter, 11.4. It's mixing with my return, and that's how I get to this 43.8, 39.8. So that state 1 entering the terminal unit is basically the supply coming out of the central unit, and again, I'm in heating mode. So that's where that comes from. And now what I see at this level is I've got that air, this coil is bringing it up to 90 degrees, and if I hover over here, I can already see the total load on this coil. Here I see the heating load determined airflow in this mode. If I look at this space, I'm still in heating mode. I can see the airflows for a heating process. Again, this is different from my cooling mode where I need 390. In heating, I only need 190 at 90 degrees entering to satisfy the heating total space sensible, which is different from my cooling. What you set up here travels downstream, and basically what you set up from the zone level or terminal unit stage, it's picking up from where we left off at the central unit to satisfy final conditions. Now, one unique thing about configuring your equipment at the terminal level that's different from the central is how you want to address this supply inlet. This option, decoupled, is not available at the central unit because we don't have kind of a supply incoming here. We have to bring in outside air, bring in return, but there's not another piece of equipment upstream of central for which we're supplying. But at the terminal unit, you do have equipment upstream. And here with decoupled, you can define how that air is entering your zones. If you do not have decoupled checked, then it's going to be coupled or ducted to this terminal unit, to this box. It's coming in and it's happening. If you select decoupled, then instead of the air being ducted directly to this box, it's going direct to the space. For this type of system, it doesn't make sense. Let's look at a different configuration, say DOAS to fan coil unit type configuration. I've got outside air coming in heating. I'm heating that up just a little bit, and then it's going to these terminal units. Because of the preset, this is already kind of reconfigured a different way. The key thing here is in this configuration, return air is on at the zone level. So return air is coming back from the zone to the terminal unit, and then it's going through a process and being supplied back to the zone. That return air is not going all the way back to the central. It's zone level return. In this scenario, we'll see sometimes your air from your central unit is ventilation, and that could either be coupled directly to this box, right? Return plenum coupled with ventilation air. It mixes in the box like we're seeing here. Let's open this up. We're seeing that here. Inlet is mixing with the return air to get a mixed state before it is heated up to supply. In other scenarios, that ventilation air is decoupled and going directly to your spaces. In this scenario, it's not mixing in the box, it's mixing in the space. And as a byproduct, your space sensible load is going to change. In this case, you will have air going direct to your space, and it may not be fully conditioned. So if at this unit, I'm only raising it up to 55 and my set point is 68, that supply air, 55, is now going here direct to space. And if I look at the cycle chart, there's that air that's entering my space. It's 55, it's dry, and my space becomes the mixing box. So before I mentioned, if you go to the details on your space, you'll see a total space sensible. Well, with decoupled, there very well may be an additional load that's introduced from partially conditioned air going into that space. You'll see that here. This is the additional load from direct outside air. And now the load determined supply is based on both your total space sensible plus the extra sensible load introduced from direct outside air. Previously, we were at 190 CFM to maintain our set point in the space. Now this has gone up a little bit because at this leaving air state of 90, we actually need to pump more air because the space itself is the mixing box. It needs to be maintained. And we have this air coming in as an additional load contributor. All right, so now that we've gone through the ins and outs of all these components and we've looked at the psychrometrics, how to actually view what you've configured psychrometrically, difference between central units and terminal units, how we're getting our airflows, what kinds of systems can be modeled with a preset, simple one-click option, and what kinds of systems need to be customized, things that should be done a little more manually. All right, presets. System A, instead of doing all this manually, I have some options, basically some easy buttons. We got air handler to VAV with reheat. We have a DOAS to a fan coil unit. We have an ERV to a fan coil unit. Single zone RTU, residential heat pump, and residential AC with furnace. Now, like configuration, even these presets are somewhat system agnostic. They're just meant to communicate a certain type of system. So air handler to VAV with reheat is pretty straightforward. I select this, and now my central unit here has outside air intake, return air coming back from all the zones, and in cooling mode, I'm doing 100% of the cooling with this air handler. But the default is 55. That goes downstream to these terminal units, where in cooling mode, nothing's happening. In heating mode, these terminal units have VAV with reheat, bringing it up to 90. And at the central unit, we even have a little bit of preheating. So if you are in SoCal and you like to do this 100% heating at the VAVs, then you can go ahead and disable this coil or delete it at the central unit. But this is the default that comes with the preset. And you'll notice that when you apply a preset, it applies it both to the central unit and the terminal units, and it sets it up for cooling and heating mode. So essentially everything does get configured to a baseline. The next one, DOAS to fan coil unit. This is outside air intake only, no return air. And then here with this DOAS, I have basically some pre-cooling, and it's really just meant to handle the ventilation load. So we're taking the outside air, we're bringing it down to space set point, like a typical space set point of 72, and then that is going downstream to these terminal units that do have the return air. So in HVAKR, with the presets, when we say FCU, fan coil unit, that can apply to many different things. It's basically shorthand for any zone level equipment that has return air coming back, and the ventilation piece may be coming from a central unit. So this is good for like VRF fan coil units, 4-pipe fan coil units, even ceiling cassettes. Even chilled beams are this kind of configuration. The return air is coming back at this zone level, space level. This is where the primary heating and cooling coils are. Anything upstream of that may be just forced ventilation, conditioned, partially conditioned, or not conditioned. So that's the concept we're trying to capture here with FCU. So terminal units have return air coming back, and in cooling mode, we've got 100% of the cooling, default to 55. In heating mode, we have 100% of the heating, default to 90, and you may have some preheat happening, some preconditioning for the ventilation that is being supplied here. Also, the default here is that the ventilation coming in is coupled. So if this is decoupled straight to space type ventilation, then you would have to go, maybe just select all these terminal units and adjust that. The air going in, click it, coupled, now it's going straight to space, and it will be adjusted as so. The ERV to fan coil unit preset is very similar, but now at the central unit, instead of having that coil pre-cooling or preheating, we just have an ERV process. And so this may temper the air just through an ERV, energy recovery or a wheel, before it goes downstream to these terminal units, which are the same configuration as before, where return air is coming back, our primary heating and cooling is happening at this box. Single zone RTU, this is pretty straightforward. The central unit basically does all the work. Typically, you won't have multiple zones served by an RTU. You'll just have one. It's going to be single zone. In this case, it doesn't matter. I've got my central unit. It's doing all of my cooling. Return air is coming back here. And then heating, it's doing all of my heating. These terminal units have nothing. It's just a piece of ductwork, right? Single zone RTU, pretty straightforward. Residential heat pump is similar to the DOAS with fan coil units. It's just in residential terms, where you're going to have an indoor unit, maybe in a closet somewhere or in an attic space, and return air is coming back to that indoor unit, and the cooling and heating is all happening there. So return air coming back to these zone level equipment, all of the cooling and heating is happening here. You may or may not have ventilation air forced coming to this zone. Sometimes it is ducted into the return air plenum. That is the default for this system. And you'll see here, we've got outside air coming in, and it is ducted straight to these indoor units. So if you've got a residential system where you don't have forced ventilation, you're not going to account for that, then you would actually want to go here and basically just delete this component. You'll have no air coming in. It's just going to be recirculating. The key thing here is with this preset residential heat pump is the heating coil here is set as direct expansion. The next preset is residential AC with furnace. Truly, the only difference is that this heating coil is called gas-fired. The rest of the configuration is all the same. All right, so those are the basic presets provided for you. For the best experience, if you're looking to get straight to your airflows and you're doing preliminary design, not a bad idea to just start with the preset, get some rough numbers. I fully expect most users to start with the preset, and then from there, dive in and start to adjust some of these numbers. My particular project, the preset of 55, it's not extracting enough latent for me. So what I might do is say, hey, all right, I want to bring this down to 50. And now I actually hit my dew point. I extract a little bit of moisture there. I have a little bit of latent load that's being handled. And that allows me to hit my SHR that I'm looking for. So the presets are meant to just get you started. And then from there, you can go in and fine tune things. All right. So now a couple of systems that are definitely not covered in the presets. First, if you have let's go back to a ERV to fan coil type system. If this inlet is straight to space, decoupled, you're going to have to decouple that manually. We don't have a decoupled preset. Next, if you have a custom air handler and you have any kind of processing to the outside air before you do your mixing and your primary cooling or heating process, That's very custom. So in that case, you would add a component in cooling mode. Say I want to do some pre-cooling to this outside air before my final cooling. Let's go ahead and add a cooling coil, and then I'm going to move it into this number 2 position. So now my outside air comes in, and here I set, let's pre-cool it to 75 degrees before we mix and then do my final cooling to 55. Let's look at the cycle chart. Here we see that happening. Outside air gets pre-cooled before the mixing occurs, and now the mix state is right here, and we bring that down to my 55 dry bulb. So that is very much a custom system. Delete. All right, the next type of custom system is if you have both a cooling and heating process happening in one mode. The most common one would be cooling for dehumidification. So this is a perfect example because in this case, I am not cooling to dew point just because of the nature of this very dry condition. And if I want to cool, I may need to pre-cool it to a very uncomfortable position for occupants. And so, hey, maybe I do that and I bring this down to 45 degrees. Now we have plenty of moisture extraction at this coil. We can see I have over half a ton of latent load happening at this coil, and I'm drying the air significantly. After this, I may want to turn on a heating coil, again in cooling mode, and reheat that air back up to a more comfortable 55 to be supplied to the space. When I add that, this is what the cycle chart looks like now. Dehumidifying, and then I bump it up again. Now I have nice dry air at 55 to supply to the space, and you can imagine a line from supply to where my set point is. That is a solid, sensible heat ratio, probably exactly what I'm looking for given these conditions. So this kind of dual cooling plus heating in the same mode, that's going to be a custom configuration, and I just showed you how to do that. While we're on this, let's go ahead and look at our reports, loads, and see how some of this information is displayed in our loads report. So looking at system A, which is what I've been using, most recent configuration was that dual cooling plus heating. Up here, I still have all my theoretical loads. This cooling sums at peak has not changed. This will populate before you even get to system design. This is a raw breakdown of all the load components present in the spaces served by this system that I've set up. If I scroll down, then I've got all this rich data showing me exactly what I've configured for cooling, and it'll walk me through each of these components. Right here, I'll be able to see the load at each of these components. So this cooling coil, I've got this as my total load, and this is the sensible piece. I even have a heating coil in this process, and it's showing me my load on the heating coil in cooling mode given this setup. If I go over here, I've got the cycle chart, and then this will give me all of the numbers, the dry bulb, wet bulb, for every state of air in this process, as well as the airflows associated with each one. 290 CFM of outside air at this condition, that maps to this point right here. Well, that's the intake. That's going to mix with my return air, and it's showing me I have this much return air at this condition, set point. This is my mixed air state, point number 2, and that's how much air is now going through because I relieved some of the excess, and that is the mixed air state. I've got that cooling process, and then I've got that heating process. So this breaks it all down for me, and I also have some checksums to go with it. So you may have a theoretical load, and then after your full configuration, you'll see your actual load on the coil based on what you've set up. So with this displayed, the last thing I want to get into is how air balancing ties into this system configuration and your coil loads. So with air balancing, your airflows, and how they affect your coil loads, let's start here. The coil loads here are driven by everything upstream, and everything upstream is driven by really these airflows. And as I mentioned before, oftentimes these airflows, like the supply air, are driven by a default, which is your load determined supply, or maybe your required ventilation if that's greater. And currently I haven't done any overrides to my air balancing. When you are looking at your configuration, you'll see a diagram view right here. And in this diagram view, say I'm looking at this office space, awesome, I can see my airflows. And if I want to, I can even override these airflows. So if something's going on, say this is a decoupled system, and I want to actually reduce my return because this outside air is going direct to space, and I'm going to be transferring it out, I can go in and I can actually start making those changes. I can say, hey, this 40 CFM, I'm going to transfer that out, and then this return is going to be reduced by 40 CFM, so we'll make that 350. That move right there just reduced the amount of return going back to my units. That changes the psychrometrics. That changes the coil load. slightly in this case, but it does affect it. Or if I'm looking at my load determined CFM and for whatever reason, I want to increase that, I'm doing some sort of supplemental calc, I want a minimum of say like 500 for this space, well, that right there also changes my psychrometrics. And when I do that, I may also want to increase the amount of return that's going back. So those kinds of changes will be reflected in these values here. You'll notice my supply air used to be, I think it was about 1900. Now it's 2080, and that changes the load on this coil. It changes the load we see here because now more airflow is going through it. There's a different outside air to return air ratio, which means the mixing state is different. This changes slightly. In some cases, it'll be more dramatic. I showed you how to do some air balancing directly from this diagram. That is not always the best place to do it because here I set transfer air, but I don't really know. It's hard to tell where that's transferring to. Next to diagram, you'll see a canvas view. This is what the old air balancing page looked like. Now we're grouping these together. They're essentially two views of the same data. The canvas view is better for balancing your airflows because you can actually see your floor plans. And if you are going to transfer air, say, out of this space, now you can see where the door is. If the idea is to do undercuts, you can say, all right, I'm transferring out of here. I can transfer in to this lobby space that is adjacent to it. Now that I'm transferring in this air, you'll see, okay, I've got a differential of 40 CFM. I can then choose to transfer it somewhere else, maybe add exhaust, or just straight up reduce the return that's possible. Or maybe I like this. I want a little bit of a positive differential in this lobby, so I eliminate infiltration. If anything, I'm getting a little bit of exfiltration, which is good. So this view canvas is one way to adjust these airflows. It's most often used with healthcare projects, lab projects, or just with projects with decoupled ventilation air, where you're supplying a surplus of air through a DOAS unit direct to space. You got to figure out how to balance these spaces if there is a significant differential. And this is just a better floor plan, kind of geographical way to do that, to map out your airflows and identify where you need to increase exhaust or increase your return air. Maybe you want to have a central exhaust in this corridor space because you have an ERV and all of this positive air coming in. You may do that. And those, again, these overrides, adjusting your design airflows, they tie directly into the psychrometrics for your zone, the psychrometrics for your system as a whole, and ultimately your coil loads. So this configuration, hand in hand with the air balancing, is an extremely powerful tool for doing full coil design, system design with airflow management all in one. It's all tied directly to your loads, and it facilitates a really smooth process moving forward when it comes time to do your dry side design in the layout step, where you're actually placing this equipment and designing your ductwork, your dry side system. And there you have it. That's the up and up on System Configuration 2.0, new and improved. If you have any questions, don't hesitate to reach out to support@hvakr.com. Hope you enjoy, and stay tuned for additional upgrades coming in the near future. Cheers.